We're now going to look at the behavior of materials in magnetic fields. Here's a figure from your textbook that divides materials between nonlinear and linear materials, and the linear materials between diamagnetic and paramagnetic materials. First, let's get a mental representation of how we would apply a field to a material. We know if we have a coil of length L and N turns, the magnetic field intensity inside the coil is Ni over L. So with the current, we can control the magnetic field intensity inside this coil. If we place our material inside the coil, we can then apply a magnetic field intensity to that material by adjusting the current through the coil. Now, B equals mu 0 times H plus M is a general expression that holds for all materials, both linear and nonlinear. But when we're working with linear materials, there's a simplification we can make to this equation. For linear materials, the magnetization is proportional to the magnetic field intensity that we are applying to that material. So the proportionality constant, chi sub m, is the magnetic susceptibility, and it is unitless because both H and M have units of amps per meter. So for our magnetization and our general expression for the magnetic flux density field, let's substitute in chi sub m times H. For M, I've substituted chi sub m times H, and now let's factor an H out. And I'm going to call 1 plus chi sub m mu sub r, where mu sub r is the relative permeability. And sometimes we just write B is equal to mu times H, where mu is the product of the permeability of free space and the relative permeability. And mu is called the absolute permeability. Here are values of relative permeabilities for the three different types of materials we will look at. Now, the diamagnetic and paramagnetic materials are linear materials, so they are well described by B equals mu sub 0 mu r times H. The ferromagnetic materials are nonlinear, so they really can't be described by mu 0 mu r times H. You have to go to this more general expression. But you do see quoted values here, and I will describe where these values come from and why it's useful to state relative permeabilities for ferromagnetic materials. The first thing to notice is that the relative permeabilities for diamagnetic materials and paramagnetic materials are very close to 1. So essentially, you can think of linear materials as being non-magnetic. The other thing to notice is that the relative permeabilities for diamagnetic materials are less than 1 but very close to 1, while the relative permeabilities for paramagnetic materials are greater than 1 but very close to 1. The entry in this table in your textbook for oxygen is not correct. The relative permeability is actually slightly greater than 1. Diamagnetic materials were discovered by Michael Faraday, and they're interesting in that the magnetic field inside a diamagnetic material is slightly less than the field that's being applied to it. In a diamagnetic material, the magnetic dipole moments from all the electron orbits and all the electron spin sum to 0. So the magnetic dipole moment associated with an atom in a diamagnetic material is 0. So your first thought would be that there would be absolutely no effect due to an applied magnetic field to a diamagnetic material. But what is observed is that the magnetic field inside a diamagnetic material is slightly less than the applied magnetic field. What we'll see is that diamagnetic materials are repelled by a magnetic field. Diamagnetism is a quantum mechanical effect that occurs in all materials. In paramagnetic and ferromagnetic materials, the weak diamagnetic repulsion is overcome by the attractive forces of the magnetic dipoles. So let's place a diamagnetic material in this magnetic field in this region right here. So we know that the magnetic flux density field inside the diamagnetic material here will be slightly less than it was in this region before we put the material here. So internal to the material will have to be a magnetic flux density field pointing in the opposite direction of the applied field. So here is that induced field, and to generate that, we have to have bound currents flowing around the perimeter of the diamagnetic material, going into the page at the top and out of the page at the bottom. Again, put the fingers of your right hand in the direction of the current flow, and your right thumb points in the direction of the magnetic field inside the diamagnetic material. So the forces on these bound currents will be given by I sub B dl cross B. So just looking at this IDL and this IDL, we see the force on this one is to the right and down, the force on this one is to the right and up, but the net effect of all these forces on all these IDLs is to repel the diamagnetic material from the magnet. Now let's look at paramagnetic materials. In paramagnetic materials, the magnetic dipole moments from the electron orbits and the spin do not quite cancel. So each atom has a magnetic dipole moment, but it is small. In the absence of an external magnetic field, the thermal vibrations result in a random orientation of all these magnetic dipole moments. So there are no magnetic effects in the absence of an external field. With an external field applied, all these magnetic dipole moments will get torqued and point in the same direction as the applied magnetic field. That will result in a slight increase in the magnetic field inside the paramagnetic material. So let's place a paramagnetic material in this magnetic field region right here. So a magnetic field will be generated inside the paramagnetic material, which will add to the applied field. So here is the resulting magnetic field due to those magnetic dipole moments all being torqued in the direction of the applied magnetic field. So the bound currents have to be flowing around the perimeter as shown here. So we can look at the forces on the I sub B dl current elements. For this one coming out of the page, the force will be to the upper left, and for this one going into the page, the force will be to the left and down. So the net result will be there will be a force that will attract the paramagnetic material to the magnet. In the next video, we'll look at demonstrations of diamagnetism and paramagnetism.